What do I want? I want the mathematize. Amazing. Okay, so is it possible or is it not possible to have values larger than 1? That's what we're looking at. And we are comparing two situations, our discrete random variables that take on a number from a list, or these continuous random variables that are some interval. Last time we did the 0 to 60, and it represented when in an hour does the doorbell ring, or when in an hour is there a flash of light. And it could be anything between 0 and 60. It could be like 5.33333. It could be any number. That's what's the difference between these. Discrete is a list, and continuous is a whole interval. Okay. For discrete ones, we're quite used to working with this probability mass function, the probability x equals x, right? Capital X, the random variable, equals lowercase x. And we called that p. What is true about the function p? P is a nice, honest, hardworking function. And what is true about it? Let's find out what you guys said. Okay. What is true about the function p? Out of 55 people, 45 people said it is not possible that p has values larger than 1. And 10 people said it is possible. And in this situation, you guys all know what's going on. It is definitely correct to say it is not possible that p has values larger than 1 because p is an honest probability, and probabilities cannot be larger than 1. I brought in a little demo to demonstrate what this thing, the way I think about this thing. Let's turn this on and put on my little demo. All right. If you are with me on this thing, I created this from Craft Supplies very early yesterday morning when my son woke up, and I have here. What is this thing? It's supposed to represent like a number line, and there are 5 possible areas that have weight. You see, there's the far left here, then 1 over, then 1 over, then 1 over. You could imagine this one is 0. Let me steal some paper here and get a pen. You could imagine this is a random variable that could be 0, plus 1, plus 2, minus 1, or minus 2. And the analogy here is that mass equals mass, mass becomes probability. And that is why it's called the probability mass function. It really is this kind of analogy. And so this probability is representing a random variable that could take on one of 5 values, either -2, -1, 0, +1, or +2. And the more mass you have, the more likely it is. So which one is the most likely? It's +1 is the most likely. And we can even calculate the probability that x equals +1 in this dopey, dumb analogy. Well, there are 3 of these weights hanging from +1. Well, how much does one weight weigh, though? I would have to get a scale and weigh it. Well, no, I don't actually, because the whole thing has to weigh 1. So because the whole thing has to weigh 1, the probability x equals anything, let's say in anywhere, that is 100%. And so therefore, since that's 100%, and there are 8 weights, 1, 2, 3, 4, 5, 6, 7, 8. 8 weights goes to 100% probability, and therefore 1 weight equals 1/8, also known as 12.5%. And so the probability x equals 1 is 3 weights, and so that is 3 out of 8, because it's 3 weights. 3 weights, and each one is 1/8. So that's my analogy for probability mass functions, and I'm trying to show you why it's called the probability mass function. You really think of it as actual little weights, little masses that live here. So little masses. Little masses. Okay, that's why it's called the probability mass function. The function p of x tells you the mass. P of 1 equals 3 out of 8 tells you this probability. This is equal to p of 1. Okay, there we go. I think I've done the analogy. Questions or comments about the analogy? It's kind of silly. You'll see why I'm so excited about it when we do the analogy for the density function. Then it's going to get real fun. But does this one make sense? People are nodding. Okay, I'm gonna move on. Let's go back. Okay, everyone got this one right, or most people got this one right, which is great. The exciting, hard one is this probability density function f. And the thing about the probability density function f is it is not as straightforward as before. Before we could just plug in p of x. Now we can't plug in. We have to do this whole trick with the area. And so we do rule 1 and rule 2 that we learned before. You mark the a and b value on the x-axis. Maybe I can zoom in a bit here while we're discussing the question. And then you have to find the area under f between a and b. And we did an example last class of this. So if I scroll up on my board, it should still be there. Okay, let's see here. Yeah, so those are the 2 rules. Highlight the part of the x-axis you're interested in between a and b, and the probability is the area under the graph. And we did the area of this little triangle thing. we did the area of this little house-looking teepee thing over here. That was the probability x is between, I think, negative a half and a half. This was the probability x is between 1 and 2. So the function f does not directly give you the probability. It gives you the height function, and then you find the area to get the probability. And what is true about this one? What is true about the function f? And this time people said, drumroll, 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 41 people said it is possible f has values larger than 1, and 14 people said it is not possible. And that is the correct answer. So phrased this way, people, I think, got the questions right. F can be larger than 1. F can be larger than 1. This is a very common misconception, and it really is all about mixing up the p and the f. The probability mass function, that cannot be larger than 1 because the total has to be 1, and each individual value is an actual probability. But f is the height of the graph. And the height of the graph can be as large as you want. It's just that the area under the graph, that's the thing that can't be larger than 1. And my analogy over here, why do people call this a probability density function? Let's go back to my dopey real-life analogy. And we'll get a new, so we'll put this one away. We'll get a new piece of paper. And we will bring out the analogy. If this was the analogy for the probability mass function, I got 5 little weights. What would be the analogy for the probability density function? It's something where the weight, instead of being concentrated in these 5 little slots, is spread out. And so I brought a pipe. This is my pipe. This is a probability density function. And you see, the thing about this pipe is there's no one part of the pipe that has all the weight. You see, the weight is all spread out. It's this long, thick tube, and it's quite hefty. You can't say, it's either 1 or 2 or 3. The mass of this thing is spread out everywhere. There's one end that's heavier than the rest. And so if I draw a little analogy here, maybe I'll put this sort of vertically upwards like that. This has a probability density function, the density function. The density, that becomes like the probability density function. The density function. And the density function in real life is in like kilograms per meter. And the probability density function in real life is in like probability per meter. I'm going to say P per meter. M here stands for meter. And so the mass, that's still the probability, like before. That's still the probability. But the difference is we are not told the mass directly. We are told the probability density function, or the density function, and you have to add it up to get the mass. So for example, what would the density function for this thing look like? Well, so on the y-axis over here, I have density. And over here, it's nice and flat. It's always the same width on this part of the pipe. So the density here is some flat function. Let me draw it in red. Red is a good thing. So the density here is some constant value. But then there's this little bit. This is the bit that attaches to your house, by the way. You see, you put this in your wall, and you screw it in over here. This is the bit that blocks animals from going in your house. So this is an important bit. It's very thick right here. And so the density function, you're putting this back, the density function is huge here. Some huge rectangle, some big spike over here. And there is no rule that says what the maximum could be. It could be as large as possible. It could go up all the way to infinity in some situations. So this is a large spike. F of x is really big. Maybe it's like bigger than 1,000 here. I don't know. Some huge number. The reason it's okay is the probability is not the density function. The probability is the total weight of this thing. How much does this little piece weigh, right? The mass, the total mass. So even though the density could be extremely high, as long as it's really thin, then the total mass is small, right? So the area here is not just f, it's f times the width. And if the width is small enough, then the density function can be as large as you want. So small width, large f values have to go with small width. The product of the width and the f, that is the mass. And that is the thing that can't be more than 1. The other fun thing about this thing is at the end over here, it's sort of got 2 pipes that are connected. And so what's going on with the density function right at the end? It's sort of a triangle shape, like we've been discussing in class. So maybe it looks like that. Yeah, that's a good approximation for what this density function looks like, drawn in red over there. And if you wanted to calculate probabilities, you'd first have to say, okay, make sure the total probability is 100%. And then you could calculate things like what is the area on one side, or what is the area on the other side, and so on. So the area becomes the mass. Probability, this is the area under the density function. That would give you the mass. So that's my analogy for this thing. And you can sort of compare the two situations. The mass is in 5 discrete bundles. And over here, the mass is all spread out. And they are kind of two different situations. Any questions or comments about the analogy? Yes, my wife saw me put this in my backpack when I did this, and she was extremely worried. But I promised I would bring it back. We need this for the house. Yes, okay.
So I was just wondering about, it keeps animals from getting in the house. So
Yes.
that is designed to keep a raccoon from getting in.
No, like an animal, like a mouse, or like a bug. So you drill a big hole in your house, and then this pipe goes in your house, and then you connect it to the water over there, and then now you have water on the outside of your house. But the thing is, when you drill a big hole in your house, you got to make sure you cover the hole up, and that's what this part does. See? Yeah.
I could say an ant could get through there.
Yes. Well, when you actually put it in your house, you have a little knob over here to make sure this hole is covered. Yes, it's being a homeowner is you got to deal with holes in your house. Okay. We're getting off topic. Questions or comments about the pipe in the context of probability? I will say there's one extra thing that you can do when you have a real-life object like this, which is you can calculate the balance point. That's called the center of mass. So let's add that to our analogy. The center, the COM, the center of mass, also known as the balance point. The balance point. And there's a fun way if you have a pipe object like this to calculate the center of mass, is you start one finger on one side and one finger on the other side, and if you bring your fingers together, then they will slowly, naturally find this balance point where the things balance. So the balance point for this pipe is right there. And you see that it's not symmetrical, right? The end on my right, on your left, is heavier than the rest of it, and so the balance point is moved towards there. That's the balance point, the center of mass. And that has an analogy in probability as well. So the balance point, let's draw it sort of on my picture. I guess it's somewhere around here is the balance point. This is the balance point. That's x equals some value. X equals some special value. And that has an analogy to probability. What's the analogy? Does anyone want to take a guess? What would be the analogy of the center of mass or the balance point of an object? What would be the analogy in probability land? Yeah. It is exactly the expected value. So if we do the expected value of x, that is the value which things will balance. It's the average x value. And so sort of the average mass of this whole thing behaves as if it's all at this point where it's balancing. And in probability class, we call that the expected value with a big bold E. We've done expected value for discrete random variables. After the midterm, we will show you how to calculate expected values for continuous random variables. But for the midterm, you only need to know how to do areas. So this stuff is post-midterm material, this little last bit. Everything else is good pre-midterm material. But we'll do this after. But it's nice to mention while I have the pipe in my hand that you can do this. All right. That's a great little analogy discussion. Last minute questions or comments about the pipe? Okay. I think that's all I wanted to say about the pipe. We did also promise you that we would go over this problem, which should be here, that I've put over here. A continuous random variable has a density like this. Oh, nobody can see it. Okay, that's good to know. Let's put the pipe down. Must not forget my pipe. Okay. A continuous random variable has a density function that looks like this. It's like a pipe where this end is like, really wide and then gets heavier and heavier towards this end. And the thing that's annoying about this problem is it has this letter k in it. And k is a variable. And the first question says, find the value of k. Find the value of k. So I'm going to take it up in a second. How many people tried this problem over the weekend? Not too many people. Okay, this is a good one. This one was literally on midterm 2 of this course last year. So this is a great kind of question to see if you know what's going on. As promised, the only thing that you need to know to do this question that is not on the page is the area of a triangle. And the area of a triangle is base times height over 2. Area of triangle equals base times height. Okay, and with a 1/2. 1/2 base times height. Hey, wait a second, that's not a triangle. That's 2 triangles. How do you find the area of 2 triangles? Maybe this is the other thing you need to know about areas is they add. So you can figure out the area of each piece individually. What's the area of that triangle over there, where its base is k and its area or its height is 0.2? So the area is of this one, of this is k times 0.2 times 1/2, and the area of this one over here, this triangle, all the way over here, is area equals 1/2 times negative 8k times 0.1. Oh, wait a second. Negative. Why am I multiplying by a negative number? Okay. Maybe there's a mistake on the board or something. I don't know. You got to puzzle it out. And also, what do I do now? Now I got the area of this one and the area of this one. How does that help me find the value of k? Like I've used the formula, but now how do I find k? Let me let you guys, since a lot of people didn't do it, let me let you think for a minute or two. Fix my mistake. How would you find the value of k? What steps would you do? And if you can really do it, find the value of k. So let's think for a minute. How? Okay. I will let you think and discuss with people near you for, let's say, a minute 30. What's your strategy? Okay, the timer has elapsed. So does anyone want to tell me how they fixed my error or what they did to find the value of k? Yeah. Yeah, this is very good. So even though the graph says negative 8k, you can't just take what you see and plug it into the formula without thinking. You got to remember what this means. So negative 8k is this coordinate, which is negative, and then this coordinate is 0. And so the difference between them is not negative 8k, but going from negative 8k to 0 is a positive 8k. So it really should be positive 8k. So that's one mistake, positive 8k, that some people will make. In general, you have to keep your head on straight. This one's nice because it starts at 0. Maybe there's some other problem where it goes from like 3k to 1k. And then you have to know that this difference is 2k. So you have to be able to do basic distances on the number line, which is a thing you have to know. All right, and then, yeah, what did you do for? Yes, okay, this is a great idea. So idea, great idea. Set the area of each triangle to 1/2. That way, the total is 1. That's one idea. Great idea. Anybody else do it a different way? Yeah. I see. So you're not convinced by setting them each to 1/2 because you think maybe one of them is actually bigger than the other one. And so what did you do? You just set the entire thing. Yeah. I see. Okay, so instead of setting each of them to a half, you added them together. So I guess now we have ideas. So this is a different idea, and the different idea is set the total area to 1. So instead of saying each one is a half and therefore the total is 1, just set the total to 1 and work it out that way. Anybody else do something different? Okay, let's take 30 seconds. I'm going to have a hand vote on these two ideas in a second, which one you think is the right way to go. So take 30 seconds and think, and then I will poll you with your hands. This is I think this is the kind of thing where, like, we told you all the rules for probability. You need to be able to put them together with logical thoughts. Like, you can't just like, oh, I'll just memorize the formula and be okay. So this is the kind of thinking you have to do to answer these kinds of questions. It's unavoidable, and you have to, you have to have your head screwed on and be thinking about it. Okay, I'll give you 10 more seconds. Okay, we're going to do a hand vote in 1 sec. I do want to emphasize, the way good mathematicians work is they do not know the answer. They do not know which idea will be the right answer until they have the idea. Good mathematicians write down lots of ideas, and then they think about them and go, hey, this one makes sense. This one doesn't make sense because of this reason. So the way you should do math problems, you should try something, and then think about it and see if it's right. So this is absolutely the right thing. Let's write down our ideas, and then we're going to figure out which one's the right way to go. I wouldn't say the one that ends up being wrong is wrong. I would say, like, it was a good thought, and we thought about it, and then we figured it out. Okay, let's vote. Who thinks the first one is correct? Who thinks the second one is correct? Okay, very good. The second one is correct. One hint, yeah, so this one is wrong because we're sort of assuming that they're equal, and there's no reason that they should be. Maybe there's a different problem where there's some hint that's given. Maybe there's a problem where they give that as a hint, right? So the second one could be a correct solution in a different problem, but for this problem, it is this one over here that is right. And another way to see it is that there's only one parameter we're solving. There's k, there's one unknown k, and so we probably have one equation. This is one equation with one unknown, one equation, and with one unknown, just like you saw in high school. Versus this one would be two equations. And so that's another hint that maybe something's not quite right. If there was more information given in the problem and there were two unknowns, then maybe it would be that one. Okay, but so let's solve. And so the equation you should get is whatever I wrote up here, 1/2 times 8k times 0.1. 1/2 times 8k times 0.1. And then the other one is 1/2 times k times 0.2. 1/2 times k times 0.2. And those together equal 1. That's an equation with k. I can factor out the k over here. I got 4 times 0.1 is 0.4. I got 1/2 times 0.2 is 0.1. 0.4 plus 0.1 times k equals 1. K times 0.5 equals 1. And therefore, k equals 2. And that is the answer. Okay. This is a real, I think if you can follow all that and do it, this is the kind of logic. You got to combine what we know in the course with basic logic of shapes and distances and that kind of thing. Any questions or comments about that one? Now it gets exciting. Now that we know k, let's figure out these things. The x is less than 0 and x is greater than 0. And once again, if you're following along, x is greater than 0 and x is less than 0. They are both areas. And in fact, they're areas we've discussed already. X is less than 0 is the area of the left thing. This is x. The area of this is the probability. Got the wrong thing. The probability x is less than 0 is this area, and the probability x is bigger than 0 is this area. Actually, I could be even more specific. It's that area plus all the area over here, which is 0. Right? X is bigger than 0 is everything to the left. Everything to the right of 0 on the number line is x is bigger than 0 in green, and in yellow is everything to the left. But of course, it's all the area under this part is 0, so it just ends up being the area of these two triangles. So in fact, these two numbers that add up to 1, these are the two probabilities we're looking for. X is less than 0 and x is bigger than 0. So we just have to plug back in to find them. So let's do that. The probability x is less than 0. This is the area where let's say under F, where x is less than 0, which is I called it, what did I make that one? Yellow area. And the formula for that was 1/2 times 8k times 0.1. So what we did in part A is still helpful, which is k times 0.4, also known as 2 times k, because k equals 2 times 0.4. And that is 0.8. So the probability is 0.8. This is a good time to check. Does that make sense? Could the probability be 0.8? Is that a thing probabilities can do? Yeah, 80%. That makes sense. Okay, so nothing obviously wrong with this. The yellow area is 0.8. And then the probability x is bigger than 0. You could do the area where it is bigger than 0, but actually there's a shortcut you can do here. That we've tried to show you this shortcut by osmosis through many practice problems rather than explicitly in the class. What's the one-line way to get the probability x is bigger than 0? Yeah. That's right. So x is bigger than 0 and x is less than 0 are almost complements. So you do have to be careful. So you could do it the other way. So you could say it's the green area, this is perfectly correct and a good sanity check. Or you could say it's 1 minus the opposite. If x is bigger than 0, it's 100% minus the opposite of x is bigger than 0. And that would be x is less than or equal to 0. And then you might be worried, we were asked for x is less than 0. We have x is less than 0, not less than or equal to 0. But for continuous probability distributions, these are the same. And so this is like a trick you can use. So for continuous distributions, the probability x equals 0 equals 0. The probability of any individual value is 0. A way you can think about that, where's my pipe? Right? If there is a slice, imagine an infinitely thin slice. What is the mass exactly at this infinitely thin slice? There is no mass there. The slice, if it's infinitely thin, will have infinitely small mass. So same thing with the probabilities of any individual point for a continuous thing is 0. So x less than or equal to 0 and x less than 0 are the same. So this is 1 minus 0.8, also known as 0.2. We could have also done it this way. It would have been 0.1 times k, which is 0.2. Either way, 20%. All right, that was A and B. Questions or comments? Okay, now it gets harder. Part C says, what is the probability that x is larger than negative 4k? And negative 8k is all the way out here. Negative 4k is halfway. So it is here, negative 4k. Okay, so that's halfway. So here is something you might do. Here's an idea. Negative 4k is halfway to negative 8k. Therefore, the probability x is less than, do we want less than negative 4k or bigger than negative 4k? Greater than negative 4k. Okay, yeah. All right. Greater than negative 4k. Should be half. Should be half as much. So maybe it's 0.4? 0.4? That's an idea. What do you think about that idea? Let's do another hand vote. I'll give you 10 seconds to think. And then you can vote. Do you think my idea is right? Or do you think my idea is wrong? Okay. Who thinks the idea is right? It's a good idea. Who thinks this idea has some problems? Okay. What's wrong with this idea? There's actually 2 different things that are wrong. Yeah. Yes. Okay, very good. Yeah, that's one of them. So I drew negative 4k over here. But remember, we're not ever dealing with sort of individual points. We're dealing with regions. And so I don't want x equals negative 4k. The probability x equals negative 4k would, of course, be 0. But the probability x is greater than negative 4k. It's not just this point. It's everything to the right of this point. So so it's actually all of this stuff. Let me do the shading in this question in part C. We actually want everything to the right over here, everything to the right. So this is all green stuff. So I completely forgot about this triangle before. That is one mistake. So I should definitely add that back in. Very good. That's one mistake. What's the other mistake? Yeah. Yes, that's very good. Why is so that is factors into why it's wrong, but why is it being a triangle? Why does that mean it's wrong? Yeah, that's right. Yeah, that's right. So this little green part of the triangle is actually a lot smaller than this yellow part of the triangle because the triangle is fatter over here, right? It's taller over here and it's smaller over here. If it was a rectangle, I could cut it in half like that. But because it's a triangle, you cannot cut it in half. So I think the safest way to do it is to draw this picture as I've drawn it over here and honestly find the base and the height and all that stuff. Fortunately, it's not too hard. This is minus 4k, which we know since k is 2, this is minus 8. And so what is the width of this guy is 8. Let me zoom in a bit here. This is getting a little hairy. Okay. So this is a triangle. The left green triangle has a width of 8. Again, don't get confused by the minus 8. That's the point over here. Minus 8 to 0 is 8. What is the height of the triangle? Oh, goodness. So here you can spend a lot of time doing equations, finding things. I like to do it with proportionality. So minus 4k is halfway to negative 8k. This is the observation I made before. That doesn't mean the areas are half and half, but it does mean the two triangles are similar triangles, and they will have half the side lengths. So the fact that the side length is 0.1 over here means the side length over here will be half that, 0.05. Okay, so there you go. I figured out the height over here by similar triangles. What about this guy over here? Well, we already did the area of this piece in a previous part. The area over here was 0.2. So what is the total area of all of the green stuff? Now I'm ready to do it. I got a triangle with 0.05 and 8, and I got a triangle whose area is 0.2. Okay. So now I can add it all up. This was not right, but instead what I got to do is the probability x is bigger than minus 4k equals the left green triangle plus the right green triangle, which is the left green triangle was 0.05 times 8 times a half, and the right green triangle we already calculated was 0.2. And so altogether, what is it? I guess this is 4 times 0.05. This is also 0.2. That's interesting. 0.2 plus 0.2. 0.4, also known as 40%. 40%. Okay. Yes, question over here in the front row.
Professor Nika, would I still get full marks if I use the first idea to get the solution?
Well, the first idea had some serious flaws. So if you did the first idea and then you found the flaws and then you fixed them, and you did something slightly different than this, you would get full marks. But if you just ran with this idea and you wrote 0.4 and you didn't recognize that this was a wrong idea, then you would not get full marks.
So what if it was a multiple choice?
Oh, that's true. I didn't realize that. Oh, if it was a multiple choice, you would have gotten us. Yeah, because it is 0. You got lucky. Yeah. But if it was a written, you would lose a lot of marks. That's an amazing coincidence. Okay. All right. Fantastic work. Questions or comments? Yeah. Here? Or? Yeah, exactly. The first idea makes 2 mistakes, right? The 2 mistakes are, I forgot about the green triangle, and I also thought that this left green is half the total yellow. And those 2 mistakes sort of cancel out, right? By forgetting the green triangle on the left, I've underestimated the value. By pretending this one is half of that one, I've overestimated the value. And by pure miracle, they work exactly to cancel out. And so the wrong idea has the right answer just by chance. I would not count on this kind of thing working out for you. That's why we do some written questions on the exam to sort of check and make sure things are actually being calculated in reasonable ways. Okay. How are we doing on time? Should we do part D? Let's do part D. Part D says, find the conditional probability. Wait a second, conditional probability, that was a midterm 1 topic. Why is there a conditional probability question on midterm 2? Well, midterm 1 was conditional probability. Between midterm 1 and midterm 2, we learned about random variables. This is a conditional probability question with random variables. Perfect question for midterm 2. Probability x is bigger than negative 4k. Okay, we have that. That's the green. Conditioned on x is less than 0. X is less than 0. X is less than 0 is everything in yellow that we had before. Let me recolor in some yellows with the highlighter so we can see our yellows, right? So now we have, oh, that's great. That's not yellow. Yellow. Right? It can be green and yellow, which is over here. So there's 2 ways to do this one. You could crunch out the formula. You could do the probability. Let's go down a bit. You know what? Let's make a copy of this and bring it down so I can write. Did my computer? Okay. Here's what we were working on. So you could crunch it out with the formula. The probability x is bigger than negative 4k and x is less than 0 divided by the probability x is less than 0. That's the conditional probability formula. And then you would recognize the top is the probability x is between 0 and negative 4k. Negative 4k is less than x is less than 0. And you divide by the probability x is less than 0. And actually, all of these things we have calculated before. Negative 4k is less than x is less than 0. That is the left green triangle. So this is left green triangle. Left green triangle divided by x is less than 0. That's the yellow, the big yellow triangle. Yellow triangle. And we have the area of both of these two things. The left green triangle we said was, what was it? 0.2. A half times 0.05 times 8. Half times 0.05 times 8. And the big yellow triangle, I don't remember how we got it, but I remember the answer was 0.8. We did that in an earlier part. Okay, so it's 0.2 divided by 0.8, which is 1/4. Very nice answer. That's the kind of straightforward way. That's what most students do, is they write out the formula, then they try to plug in the formulas. It's totally valid, totally legit. You could do it a little bit more sneakily, which is you could remember when someone says x is less than 0, when they condition on x is less than 0. So this is the sneaky way, I guess. Sneaky. This is like a more fundamental understanding of what conditional probability is. X is less than 0. The probability of anything given x is less than 0 means cut away all else other than x is less than 0. So when someone says, please find the probability of x is something given x is less than 0, then we can take our scissors and we can go to our picture, and we can cut away everything that doesn't have x is less than 0. So we can take our scissors, cut this away, and so the new picture in this sneaky way of thinking about it looks like this. There is only one triangle like this. There was this thing at negative 4k, and there's this thing at negative 8k. This was the left green triangle over here. And then the big yellow triangle was everything over here. Big yellow. Okay. So if you know this way of thinking, now you just have this picture of the triangle. And if you stare at this picture of the triangle, you can see that the answer is 1/4 by several methods. One is, again, you could calculate the heights over here. You could do this little picture, draw this. Now there's 4 triangles that are equally sized. There's the green triangle, it's copy, it's copy, and it's copy. And so therefore, left green, over yellow equals 1/4, by looking at the picture. You could also say, the height shrunk by a factor of 2, the base shrunk by a factor of 2, therefore the area shrunk by a factor of 4. Height shrunk by 0.5, base shrunk by 0.5. Therefore, area, which is base times height, 1/2 base times height, shrunk by 0.5 times 0.5, which is 1/4. All of these are sort of more intuitive ways to get at the answer, where you don't really need to know anything. You'll notice I never used the value of k in this thing. I never had to find the actual area of the yellow triangle in these sneaky methods. If you don't like the sneaky methods, this way is perfectly good as well. Maybe it will take you a little bit longer, but that's perfectly fine. Okay, that's a very deep dive into question 4. Yes, another question from the front row.
Professor Nika.
Yeah.
In your solution, I noticed you kept the k in there.
Yeah.
But if you solved it in A, couldn't I just simplify the question?
Yes, that would be fine. The nice thing about leaving it as k and only putting it in at the last second when I need it is if I made a mistake earlier on, it's easier to fix later, and it's easier for the grader to see that I'm doing everything right. So if you make a mistake in the value of k in part A, and then you use that mistake everywhere, then things will get messy and you will forget where things came from. So it's a good tip to plug in as late as possible. This is a good tip in physics class as well.
But we could check there.
Yes,
Are
you saying,
right?
did I make a mistake? Oh, okay. Yeah, all right. Yeah, you can use this to double check that the k is correct as well. Is that what you're?
Well, I'm just saying that, you know, you don't need to keep the -4.
Yes, that's true. Yeah, you could have written this. This is I used to, when I was an undergrad, I was in physics, and in physics we had to keep the constants around till the last second. Otherwise things would get very messy, and you wouldn't be able to check the units. So this is a habit I picked up, I guess, from the physics team. But I think it's good. I like doing it this way. Yeah, if you wanted to put in -16 and -8, that'd be perfectly fine. Okay. Other questions or comments from someone else? All right. So the midterms on Wednesday, make sure you do lots of practice problems. On Wednesday's class, we'll have more review for you. There won't be any new material on Wednesday or anything like that, just like there was no real new material today, just practicing some old stuff and clarifying. But we'll see everyone Wednesday night, and good luck on the midterm.